Welcome to MathGPT. Today, we're going to talk about two important concepts in vector calculus: flow integrals and circulation. These concepts are particularly important in fluid dynamics and electromagnetic theory. Let's start with the definition of a flow integral, also known as a line integral of a vector field. A flow integral measures the extent to which a vector field aligns with a given curve. It generalizes the concept of integrating a scalar function along a curve to vector fields. Mathematically, if we have a vector field f of x, y, z, and a smooth curve c parameterized by the vector function r of t, where t ranges from a to b, the flow integral is written as the integral of f dot d r along curve c, which equals the integral from a to b of f evaluated at r of t dot product with r prime of t dt. Here, f evaluated at r of t is the vector field at points on the curve, and r prime of t is the tangent vector to the curve at those points. The dot product measures how much the vector field aligns with the direction of the curve. Let's understand the physical interpretation of a flow integral. If F represents a force field, the flow integral gives the work done by the force on a particle moving along curve C. If F represents the velocity field of a fluid, the flow integral measures how much the fluid is flowing along the curve. Let's visualize this with a simple example. Imagine a river with a current flowing in various directions. The arrows represent the velocity field of the water. Now, let's add a curve through this river. The flow integral would measure the total flow of water along this path. Notice that at each point, we only consider the component of the velocity that's parallel to our curve. Components perpendicular to the curve don't contribute to the flow. The flow integral sums up these parallel components along the entire curve. Now, let's move on to circulation, which is a special case of the flow integral. Circulation is the flow integral evaluated over a closed loop. It measures the tendency of a vector field to circulate or rotate around the loop. Mathematically, the circulation of a vector field f around a closed loop C is written as the closed loop integral of f dot dr. Notice the circle on the integral sign, which indicates that we're integrating over a closed loop. In fluid dynamics, if F represents the velocity field of a fluid, the circulation gives a measure of the amount of vorticity or rotation enclosed by the loop. A non-zero circulation indicates a net rotational motion of the fluid around the loop. Let's visualize circulation with a rotational vector field. Here's a vector field defined by f of x, y equals negative y, x. Notice how the vectors rotate around the origin, forming a counterclockwise circulation pattern. Now let's add a closed loop, a circle around the origin. The circulation would measure the tendency of the vector field to rotate around this loop. At each point on the loop, we consider the component of the vector field that's tangent to our loop. In this case, the vector field aligns perfectly with the tangent direction of our circle, giving a positive contribution at every point. For this specific example, the circulation around the unit circle is 2 pi, which is positive, indicating a counterclockwise rotation of the vector field. If we consider a different loop or a vector field with a different pattern, the circulation might be different or even zero. The concepts of flow, integral, and circulation are closely related to a fundamental theorem in vector calculus known as Stokes' theorem. Stokes' theorem states that the circulation of a vector field around a closed loop equals the flux of the curl of the vector field through any surface bounded by that loop. Mathematically, it's written as the closed loop integral of f dot d r equals the double integral over the surface S of the curl of f dot ds. The curl of a vector field, denoted by curl f or del cross f, measures the rotational tendency of the vector field at each point. Stokes' theorem thus relates the circulation around a loop to the total rotation within the loop as measured by the curl. Let's explore some practical applications of flow integrals and circulation. In fluid dynamics, circulation is used to analyze vortices and the lift generated by airfoils. The famous Kutta-Joukowsky theorem relates the lift force on an airfoil to the circulation around it. In electromagnetism, flow integrals help us understand electric and magnetic fields. Ampere's law, which relates the magnetic field to the current it encloses, is essentially a statement about circulation. In thermodynamics, the work done by a system can be expressed as a flow integral of pressure with respect to volume. More generally, flow integrals and circulation are fundamental tools in vector calculus used to analyze and understand vector fields in various physical contexts. Let's summarize what we've learned about flow integrals and circulation. The flow integral measures how much a vector field aligns with a curve. It's calculated as the dot product of the vector field with the tangent vector to the curve, integrated along the entire curve. Circulation is a special case of the flow integral, where the curve is a closed loop. It measures the rotational tendency of the vector field around the loop. The key difference is that circulation is specifically defined for closed loops, while flow integrals can be defined for any curve. Both concepts are crucial in understanding vector fields, especially in fluid dynamics, electromagnetism, and other areas of physics. Thank you for watching this video on flow integrals and circulation. I hope you now have a better understanding of these important concepts in vector calculus.